let's do it. Any questions? Just update. I just sent out all the questions and answers as if we would have played Jeopardy. And so this is something that was a shock to some people who came and picked up their exam 2s to find out that a lot of the fill-in-the-blank questions and answers were already given to them in the form of an email that included the Jeopardy questions and answers. So once again, because of that, I once again remind you that I highly suggest taking a look at the questions and answers from the Jeopardy, which I just emailed to you, because those are going to be good examples of fill-in-the-blank questions. In fact, I'll probably from that pick 50% of them and use them actually on the exam. So that's a good precursor or a good way to prepare for the exam. Further, there's been some people that made some key term lists, and they've been darn good, so I don't know if they've shared them or not, but I highly suggest go ahead and make a key term list and study the terms to make sure you know all the potential fill-in-the-blank questions. Also, when we look at the multiple choice questions, where am I pulling the multiple choice questions from? About half of the multiple choice questions that will be on the exam actually are ones that come from the quizzes. And so the quizzes, not every single, quizzes, you'll take a quiz, it's a 5-question quiz, you'll get probably, of those, there's probably about 40 total questions, and it randomly picks 5. So yeah, you're not going to get all of them. But if you maybe work with some other people, you start comparing and contrasting different multiple choice questions, then you should get a good base as far as having a good number of multiple choice questions that could or likely will be on the exam. Finally, like always, we've got the written responses, and I've already had 3 students send me their written out responses, and I critique them as, I suggest you look at this, or you're giving me way too much information here. I try to help as far as being able to prepare you as best as possible for getting a full credit, a 5 out of 5 for each one. All right, questions?
For the first essay question, the theory of the continental drift, he also talks about Pangea, how you say it, and then the tectonic plates. Is that all included in that, or is it just supposed to talk about the continental drift? Separating from Africa?
Right, so all of that.
Okay.
So all of these questions, just in general, more broadly speaking, give me as much as you can. So always kind of think, well, should I talk about this? Well, yeah, go for it, because it doesn't hurt to give me too much information. But in answering that first top question, describe Alfred Wegener's theory of continental drift, include several examples of evidence to support his theory. Some key terms that you have to mention. You have to mention first off plate tectonics. So the idea that we have these plates that are moving across Earth's surface. You don't really have to get into the asthenosphere and all of that, the lithosphere, but if you include that, that only helps. It only enhances your response. But some things you definitely have to explain and talk about is continental drift. And as you mentioned, the key thing with continental drift is the continents are drifting away, for the most part, from Africa. Africa's remained fairly stationary. Meanwhile, all the continents have split up and broken off from Africa. And so when we have that, where they broke, before they broke off, they're all one supercontinent. That's Pangea, whatever it's called. So then explaining some evidence that supports this guy's theory. Because this is a theory that I think he came out with in the 1930s, and then there was a bunch of wars, and so no one was really talking about it. Then all of a sudden, in the 1960s, people come back to this guy's article and like, yeah, this actually makes a lot of sense. So it wasn't until later till his theory was actually proven. And so one simple way to prove his theory is if you look at the continents and you kind of put them back together, they fit together very much like a puzzle piece. So that was the first kind of evidence of his theory, and kind of what I talked about in the video lecture, how South America is the little spoon, and Africa is the big spoon. They're kind of cuddling each other, and you can see how it's almost a perfect shape right here as far as this part of Africa and that part of South America. Other evidence of this is the United States. The United States, we kind of move everything back together, northwestern Africa and the Atlantic coast of the United States kind of match up nicely together. So that's one way to support with examples of evidence of his theory. Other ways to showcase or support his theories is the fact that there's certain fossils, certain bones from things that are long been dead that could never migrate across a big ocean like that. There's no way they could get all the way. They're animals that could never actually swim across a major ocean. Obviously, there's no boats they can jump on and cruise across the ocean. So that's further evidence. As you found fossils found in this area of Africa, and similar fossils found in that area of South America, further proof that those all must have been together at one time. So the puzzle pieces and combined with the fossils. What else? Other evidence of his theory. Maybe I've mentioned.
The Atlas and the Appalachian Mountains.
So yeah, so you can go back and look at the actual formation of mountains. And so the Atlas Mountains. So the Atlas Mountains are these mountains from an old map quiz that we probably never did. That map quiz would have revealed the Atlas Mountains are those mountain chain in the northern part of Africa. They actually were formed way back when Africa was bumping up against the United States, and those formed also the Appalachian Mountains. And so the same, essentially, orogenesis, or mountain building movement, or mountain building moment occurred way back when those continents were all together and they were bumping up against each other before divergence across the Atlantic Sea, Atlantic Ocean caused it seafloor spreading and thus separated the continents. Other evidence that this is a question that, if I recall, I probably shouldn't be telling you this, but this is the one that people on average do the best. And I think it's because you got, third grade, you got hit with this stuff. In fifth grade, you got hit again with it. Seventh grade, eighth grade, ninth grade. And so you kind of get stuck in the head. So during all those years, even while you're texting the entire time during your high school classes, you still somewhat probably got that information in the head. So I think on average, people know that one pretty darn good. Anything else I can expand on that?
Divergence is still occurring, right?
Still occurring, yes. In fact, we're about 250 million years away from all the continents coming back around and coming together to form another supercontinent. And we'll be there, right?
Yeah.
All right. So other examples, since you guys all know about Madagascar, since that's that movie you watched as kids, Madagascar kind of fits nicely in there. And it's more evidence that the plates are separating. So Madagascar used to be part of Africa. So also going on, and actually really typically soon, in the next 50 million years, Africa is going to start breaking open. The Indian Ocean is going to come into the interior there. So that's what these lakes here are, these big rifts, big divergence. It's separating, and then because they get a whole, don't cuss Andy, whole lot of rain, they also then fill these cracks, these little, these crevices with fresh water that then creates lakes. All right, get that one? Anything else from that one? From your notes that maybe I didn't mention just now? I think I kind of gave away that it's a question I like to ask. Yeah.
So I wrote everything just about his theories and stuff, we're supposed to do, you said do both of them. But what were we talking about where we should definitely say about the plate tectonics? Oh, some key things to mention is to say the word plate tectonics.
So that's just mentioning it. The idea that on top of the asthenosphere are these plates that are moving. And so that's the first thing you had to mention. And then explaining continental drift. I know it's kind of obvious what it is. It's continents drifting apart. But kind of explain a little bit more about that. Give me a little bit more, 2 sentences maybe, explaining continental drift. Key to understanding continental drift is divergent plates. That's what kickstarts and separates and kickstarts the movement of plates. And then we get collisions and fault and all of that. And then other things is, give me evidence, give me at least 2 different things. So we mentioned the formation of certain mountains. We mentioned the fact they fit like puzzle pieces. We've mentioned the fact that there's only fossils found in certain parts of these continents that are way far away, which is further evidence that at one time all those fossils were together as that habitat was shared by whatever the thing might be.
Okay.
Cool. All right. Next up. We can talk about anything. Yeah.
Can we talk about the hot spots?
Yeah. And so this is go back to that demonstration I did. So it might have not been successful, it might have floundered. Maybe since I have a pin that works, maybe we could do it right now. But the idea here is we've got, first off, we have to think about hot spots. They do not move. They are fixed. They stay in one spot. So what happens is we think about our lithosphere. Our lithosphere, as we just learned, tectonic plates, they move. So what happens with these hot spots are, they don't move, but they flare up. So essentially we think of that like a lava lamp. Which if you stare at a lava lamp long enough, you'll see that the lava always kind of bubbles up. That makes sense. It's convection, warm air rising, same ideas apply. So what happens is this little breach, this little crack in, let's say, the asthenosphere allows magma to come up, pouring through the asthenosphere so that it eventually pokes up into the lithosphere. If it eventually pokes up far enough, it'll actually create an island. So it'll create a high island or a volcanic island from this magma that fires up and brings this magma to the surface. But over time, it might die down. And we're used to this. I mean, an example of a hot spot is Old Faithful. I don't know, has anybody seen Old Faithful in person? It's that geyser / geyser, whatever, I don't know how to pronounce it. It's that geyser. So it's out in Yosemite. It's a hot spot. Same idea, but instead of it creating an island, it just creates steam. So that particular hot spot, if you've ever been to it, you don't see it spewing out all of that steam all the time. It's a very, it happens, once a day, maybe twice a day. So you kind of showcase how these things flare up and then die down. But at the bigger scale, when we think about hot spots, they fire up. But once again, plates, they move. So when it dies down, essentially what happens as this plate moves, this island here just kind of moves with it, and then essentially carries on. Then the hot spot fires up again, creating another island. And so it then fires up, creating another high island. And essentially, once again, the plate moves. And so then we have another island that forms. And so essentially what hot spots do is because they don't move, but over on top of them, the plates do move, the tectonic plates do move, they then create, on average, if we look at it from the aerial view, they create these chain of islands. And so if this is the hot spot right here, the hot spot's located right there, we know that this plate, we can look back at deductive reasoning and see how this plate has moved over time. Because of these same islands that all formed by going over that one hot spot. So these are the oldest over here. They formed a long, long time ago. And the youngest would be the one right over the hot spot. They'd be right smack down on top of it. In fact, Hawaii, here's the shape of Hawaii, each island gets a little bit bigger. So what's happening is right now, the hot spot's over here, it's creating a new island. And that new island's massive, but it's underwater. And so it's not really, we don't really talk about it, or anything like that. So all of these islands formed over that one hot spot. So you can look at the Hawaiian Islands, you've got the oldest and the youngest. Does that help?
Yeah.
And so go.
The biggest will always be the youngest?
Yeah. Why?
Has an
Erosion weathering. So essentially, all of them were the same big bad self, but over time, just like me, they've been broken down, they're weathered and eroded away, and they're nothing like they used to be. So they've been broken down, they're much smaller. So in fact, the ones that are, if you look at the entire Pacific Ocean, we can't see them. But these here, all of these are essentially underwater. They've been worn down so much, and they're underwater islands called seamounts, underwater mountains, let's say. So, anyway. So if the demonstration, if you recall, but yeah, you're one of the people that helped out, but my pen didn't work. But essentially what you guys were showcasing the movement of the plate. I wasn't moving, I was firing up and then dying down. And if we would have looked at it, we would have seen a chain of islands, with the oldest the farthest away from me, the hot spot.
Did you say that the magma pushes that up?
Yeah, I'm not really good with that stuff as far as the inner workings of all that material. But just think of it, if it's underground, hot molten material, it's called magma. Once it breaks the surface, it's then called lava. And so it's that magma, all of that goop that's essentially been heated up is rising, and it's just a crack. It goes wherever there's a space, wherever there's a vent. So there's these little cracks. And they don't move, and the hot spot's been created, and essentially they come up through that crack, that crevice. Oh. Yeah.
So then for the Hawaiian Island chain, do you want us to give specific examples about that in general, like the general location it's going because of the hotspot and?
Yeah. I mean, you can add that. Yeah. I go like the same to Hannah's question. I mean, as much as you can, really. I mean, if you're kind of thinking, well, should I talk about this? Yeah, go ahead. Because you guys actually probably know more of this stuff than you realize. It's one of those deals, once you start writing, you're like, yeah, okay, you know, it's kind of, I don't know. It's one of those deals where I notice it in lab. When I do the lab, it's kind of people kind of, they like, it hits them after they answer the question. Like, oh yeah, that's right, I get that. So it's the same idea. It's with stuff that you already know, it's just kind of pulling it out of there. Other questions? Keep them going. Yeah.
Can you figure out just a basic definition of karst?
Karst.
Like, I understand all the different like examples of the features, but like if you just had like 5 or 6 word definition.
Yeah, all right. Putting me on the spot here. Karst, that's fine though. I love it. Karst, chemical weathering. Let's say chemical weathering. So there's another key term, chemical weathering of limestone, but it can be really any soft sedimentary rock. So chemical weathering of limestone from, man, I know this is more than 5 words, but from carbonation, and carbonation is a type of chemical weathering, from carbonation over lots of time. So that's the process. It's chemical weathering. So it's chemical weathering, and the examples I give, I can't remember if I gave it, but you know, if I right now got out my hydrochloric acid and I just said, all right, screw it, I'm just going to start pouring this on my skin, what would happen? It'd burn. Essentially, the hydrochloric acid would be eating away at my skin. Kind of the same idea applies to karst as far as what happens. And so carbonation essentially slowly eats away at that limestone, just like that hydrochloric acid eats away at my skin. So chemical weathering via carbonation. So what happens, just go ahead and we'll just answer that question as we're talking about it. So where are we at? Describe the karst landscapes and landform features found in South Central Indiana, including an explanation regarding how karst forms. So if you ever had to tell me how karst forms, you have to tell me 3 things. So the first thing is you need underlying bedrock. So you need bedrock. So you need underlying bedrock, and preferably we want it to be soft. If we want karst features, we want it to be soft bedrock. It's easily weathered material. So that's the first thing. And so throughout Indiana, we've got a lot of limestone. In fact, from corner to corner of our state, we've got limestone. However, there's just a little sliver of the state, from about Bloomington all the way down south through Corydon, through Salem, Bedford, South Central Indiana. We've got an area that's never really had glaciers come over it. So because of that, the bedrock, the limestone, is very close to the surface. And so because it's so close to the surface, it's easily weathered away. So what it means is it's easily interacting with the overlying air, and more importantly, rain, precipitation. So the second thing we need precipitation plus something. What do we need? Precipitation plus carbonation or carbon. So where is precipitation? Where is rain going to pick up carbon? I don't know if you've ever heard of something called carbon dioxide that's in the air. That's one place it can pick up carbon. And so as that rainwater comes down from the sky, precipitation, once again, karst, we're probably only going to find in the eastern part of the country because it rains more here than it does in the western part of the country. And so because of that, the rainwater comes, picks up carbon, picks it up kind of like an Uber, picks it up, and then takes it to the surface. It eventually picks up even more carbon because we have carbon in our soil. So carbon, essentially pretty much everything that lives and dies has carbon in it. So what we have is we have precipitation that picks up carbon from the atmosphere, but also from the ground, that then turns into a slightly carbonic acid, turns into a lightly acidic, sound intelligent, Andy, lightly acidic form. So essentially what we got going on is carbonation. So precipitation plus picking up some carbon equals carbonation, so it turns it slightly acidic, so that it can then do the weathering. The third, and probably the most depressing thing in life, time. Requires a long, long time. So the example I used beforehand, the hydrochloric acid, that's instantaneous. This is a very long, slow process. Chemical weathering, in case of creating these karst landscapes, takes a long, long time. So now let's talk about how landform features. So some landform features. How many do you want to talk about? Let's talk about 3 of them maybe? Sure. Let's talk, the first one is sinkholes. Probably the one that's the most important. So sinkholes. And so I don't know how I describe this in the video lectures, but this essentially we've got this underlying bedrock. So this underlying bedrock, all of this is limestone. However, at one time this area was flooded. So this area was flooded, and so essentially this cave, this cavern got real big. This underground area, below ground. It's full of water, especially if you think about all those glaciers melting. It's going to fill up every crack and crevice in the underlying bedrock. It's going to only increase the size of that underlying bedrock. However, we'll say over time, the water table goes down. Let's use an eraser. PhD boy. All right. So what we got is we got this water table that then goes down. So essentially what happened is now we can then essentially go freely in these little cracks and crevices, and those are caves. So caving, when you go caving, you're essentially playing in areas, these little cracks and crevices that have been opened over time because of massive amounts of karst, massive amounts of carbonation that's opened and created these passageways and make it bigger and bigger and bigger. But then the water table drops, and then then you can go freely frolic in there and store moonshine, drugs, whatever. So what ends up happening over time is chemical weathering slowly makes this cavern, let's say, get bigger and bigger and bigger. So what happens is over time, then the overlying land can't be supported by that. It's essentially, this gets more fragile and fragile and fragile. And so what happens is this big, huge cavern eventually collapses because it can't hold the overlying land. And so essentially what happens is it then collapses. And then of course what happens above it, it also collapses as well, creating these sinkholes. So when we think about news stories, whenever they talk about sinkholes, it's typically two places. It's either in Florida. You always hear about Florida and sinkholes. I think about this time this time last year, there was a guy who was, I think, hanging out with his brother or something, and his whole entire house went into a big giant sinkhole where then I think they never even found him. They just said, screw it, just leave him down there. It's too difficult to go down there. There's been another more recent one, I believe, which is the Corvette Museum in Bowling Green, Kentucky, in which a sinkhole occurred there. So it's only in areas where you have limestone close to the surface. So it makes sense that we're going to have a ton of limestone there in Florida, Because what is limestone? It's essentially sediment from a shallow sea, all the various organisms and fossils all coming together and compacting into rock. So down there you're going to get a lot. In unglaciated Kentucky, there's a lot of limestone close to the surface, and also there in south central Indiana. So sinkholes essentially are when a cave or cavern collapses and then brings with it the overlying land that can no longer be supported by that big, huge open area. When you have several sinkholes together, what ends up happening is it kind of creates this fake valley. It creates this fake valley, which you have several sinkholes together. So it kind of creates, I'm not really drawing it well, but so it kind of creates this situation where you have several sinkholes together going to then cause the land to collapse. That's an awful drawing. But I do probably a good job with the video lecture. So talking about karst valleys, which are just a chain of sinkholes together that creates this long linear depression instead of just one, almost like a golf ball dimple depression. So you see a lot of these in south central Indiana, like I said, south of Bloomington especially, a lot of sinkholes. Other things. Help me out here. Oh yeah, disappearing and lost streams. Yeah. So springs, and so what happens is this is kind of an aerial view of Indiana. So what happens is you might have a stream kind of disappear because it disappears into a sinkhole, and then the ground continues on, it comes back somewhere else, and so it all of a sudden reappears. So those are what we call lost streams. There's several of those in south central Indiana that just kind of disappear, but then come back somewhere else. It's just kind of a stream going down into a sinkhole. Any more on that one I need to explain? All right, what we got next?
We talked about stream transportation.
Yeah. All right, so stream transportation. So that's all part of, describe several characteristics of stream transportation, including flow and channel characteristics. All right. So the first thing we have to think about is as far as our sediments. So what are our 4 different types of sediments in terms of different sizes, from biggest to smallest?
Clay.
Biggest to smallest.
Oh, big gravel.
Gravel. So gravel's our biggest. Then we've got sand.
And silt.
Then we've got silt.
And clay.
And then clay. And so this is kind of an obvious, but water, flowing water, the faster water moves, the more it can move stuff. It can move and pick up bigger stuff. So essentially, we think about a stream, we can think about its flow. First off, kind of from the cross-section view. So we've got the top, the surface, and then the underlying bottom, the bottom of the river. So we've got these 3 zones that we can predictably find these location of these different types of sediments. First off, we've got at the bottom bed load. So bed load is the big stuff. So gravel, sand. Sometimes gravel can even be moved because if the flow of the river isn't fast enough, it's not going to move the big gravels. But it's going to move the sand, it's going to move the bigger pebbles, and they're going to kind of scoot along the bottom. So they kind of scoot along the bottom of the river, and they do all kinds of erosion as they skip and bump into other big rocks, other big pebbles, and so on. Then we have our next area, and that's called the suspended load. So this is going to be more of the silts and the clays. So the silts and the clays are held up aloft, they're light enough to be held up aloft, so they're further going to move a farther distance because they're not just kind of rubbing up slowly here on the bottom of the stream. So this is the side view. Finally, we've got our third area. It's kind of found throughout, but you're more likely to find it at the top compared to the other ones, and that's the dissolved load. And so we think about chemical weathering, essentially eating away at the underlying rock. It's going to turn water into kind of a milky color. as that weathering, as it kind of breaks stuff down into a solution. And so that's going to kind of help to explain why rivers are always kind of dirty, muddy looking because of a lot of that dissolved along with the suspended load. So that's from the side view. We can also think about the profile, the general profile of a mountain or a big entire watershed. Where do I want to go? This one's gone. So we think about the general profile of a river. So we have its headwaters up in a steep slope area. Then when it starts to gently even out till eventually it gets to an ocean. So the mouth, let's say. We'll call that the mouth, and we'll call this the headwaters or the origin of a river. And so we think about the slope. Of course, if I right now, hell, I'm going to do it. So if I pour this water on this table, notice where it goes. We don't know where it's going to go. So I have it over there. So if I gently pull up, it's like Plinko. Who knows where it's going to go? Anyone know Plinko, the game on Price is Right? But if I increase the steepness of the slope, so I raise it up, we have a good idea where it's going to go. It's going to go straight down the slope here. I mean, it's going to go straight down. And so as I increase the slope, essentially it straightens out the flow of the river. Whereas I lessen the slope, it creates more of a meander. We have no idea where the river's going to go. And so we can apply that to the same idea here. Steeper slopes, the rivers are going to be much more narrow. The streams are going to be more narrow, but also straighter. As straight as they can be in nature. So essentially what we got going on is we can get these very rapid moving waters that we find along a steep slope. But what happens is, eventually, the slope starts to level out. So what happens then is the pace of this river slows down. The flow of it slows down. And so it can't carry as much. And so what ends up happening is we got big rocks and gravels and all of that pretty much stay up at the top. And so all of this, when we go whitewater rafting, we like going over the rocks, the rapids, because it adds to the excitement. But they don't go whitewater rafting down the Ohio River because it's very slow moving. It starts to slope, evens out, and further there's no big boulders and rocks and all that. Anyway, and so what ends up happening is the gravel, the first one, is essentially removed up at these higher elevations with these steeper slopes of this general profile. Eventually what happens is it starts to level off, and so then the sands start to cluster. And then eventually what ends up happening is the silts and the clays, the smallest little particles, are the ones carried the farthest. They eventually dump down into the ocean. So that's kind of the general profile of it when we look at the big picture area of a stream. Damn, I don't know if I've ever asked this question, but it's loaded. This would take probably 3 pages to write about. But then finally, we look at the flow characteristic, and that's where would we expect the water to be moving the fastest. Why do we care about that? The faster it moves, the more erosive it can be, the more destructive it can be, the more damage it can do, the more changing of landforms that can be done. So when we think about the general profile of the stream, this is once again looking at the side view. So let's say we look at a channel. Here's the shore, here's the other shore, here's the surface. We can go ahead and predict and identify where we would expect the fastest flow of this river to be. It's going to be above the deepest part of the channel. So this is the deepest part of the channel, it's going to be above it. It's going to be just below the surface. Why is it just below the surface? It's because we have friction, resistance from the air above. That's going to slow down the water. However, just below the surface, just below that friction, is where we would expect a faster flow of this general river to be. Now we look at the aerial view. So we look at the meander. So the general direction is, if it's in a straight line, we can pretty much predict it's going to be the fastest flow of this river is going to be right in the middle. However, when we get to a meander, what happens is the deepest part, but also the flow, essentially is more outside, more closer to the outside of this meander than the inside. So that's where we would expect the flow to be faster, closer to the shoreline over here. And then essentially it switches, and it's now over there on this outside meander. So it's always on the outside of the meanders where the flow is going to be the fastest. Subsequently, what happens is this is where more erosion is going to occur. And so this creates those cut banks. Those very, very steep slopes that are created from erosion, this fast-moving water, ripping in through here and cutting away and carving out that particular landform, that erosive landform. Whereas in the inner part is where the point bar deposits cluster, and that's answering a different question. Next. Next. Anyone?
Will we have any images to look at?
In
the last couple we've had 2 on each.
Yeah, there'll be probably 2. I haven't made it yet, so can't remember what I did last year. An example of one, I would have a picture of the Hawaiian Islands. I would show the location of the hot spot, and I would ask you A, B, C, or D. Which one of these is the oldest? That might be a hypothetical. Once again, I haven't made it yet, and too many brain cells ago, as far as when I made it, so I have no idea.
Can we talk about the last question about the Indiana?
Yeah, let's talk about the 5 specific landforms. So in the case of Indiana, as far as we've been heavily influenced, as far as what has shaped our landforms, what has created the landscape that we see in our state, overwhelmingly it's glaciers. Glaciers are nature's bulldozer. And so whenever you talk about Indiana's glacier activity, you first off have to talk about continental glaciers. So be able to explain what continental glaciers are, generally from whatever the notes say. So continental glacier, so being able to explain what it is, how big it is, it's entire continent wide, it's in parts up to a mile tall. Just imagine from the surface above up straight up a mile. That'd been a whole different Mile High Club back then. But anyway, so the Continental Glacier, huge feature. Compared to an Alpine Glacier, Mountain Glacier, much smaller. It's going to be more confined to mountainous areas, obviously. The Continental Glacier, the one in effect in Indiana, the most recent, about what, 10 to 12,000 years ago? Is that about when it was? So about 10 to 12,000 years ago is when the Continental Glacier was right over us here at Naptow. So that's the first day talking about Continental Glacier. Then we have our 5 different landforms to talk about. And I'll go ahead and no particular order, just go ahead and list them. So we have our first one, the end moraine. Second one, recessional. Third, we've got till plain. Fourth, the outwash plain. And then the last one, kettle lakes. So being able to identify each of those as features, kettle lakes is at the end, apologize. But those 5 having to first off identify and being able to lightly talk about how they formed. And I'll go through each of those right now. So the end moraine. If you can recall the end moraine from last lecture, that's essentially the potato chips. Remember I pushed the potato chips, I took all that crap, I pushed it, and then the glacier stopped. At the edge or the boundary of that glacier movement, it creates end moraines. It creates that rugged topography, that linear feature that's along the extent of a glacier boundary. Next up, we have the recessional moraines, which are always found behind the end moraine. So essentially we think about this Continental Glacier moves this way and then it retreats. And when it retreats, that's when it then creates the recessional moraines. And all the recessional moraines are just, a few thousand years, a few hundred years of cooling, which causes them to advance. That's more snowfall, which adds to the weight, which causes them to advance. And when they advance, they create mini end moraines. Smaller versions of end moraines. And so what happens is you have these parallel features that you'll note if you look at the topographic map of Indiana from about Anderson all the way up to Fort Wayne. You'll see these parallel ridges which is formed as that glacier is retreated, advanced, moved back, retreated, advanced on its way back to where its current state is, its current location, Greenland. So the same ice sheet, the same Continental Glacier that's over Indiana 10,000 years ago is now up in Greenland. It doesn't really retreat, it doesn't turn back and head the other direction, it just melts. And so that's recessional moraine. Also, always behind the end moraine, we think about glaciers. They pulverize everything in spot. So any valleys, any hills are essentially filled in with sediment. So one thing you'll notice in these areas that aren't moraines, they don't have recessional moraines, you'll find very, very, very flat surfaces. That's why northern Indiana is so flat. It's so flat because the glaciers essentially come through here and essentially flatten everything out. It's filled in the hills and the valleys with sediment, and now you kind of have gently rolling topography that's rather flat, which is great for agriculture. So till plain, great for ag, which is why we have so much abundant ag in that particular area of the state. Next up is outwash plain. So outwash plain, where till plain is behind the continental boundary of the end moraine, outwash plain, on average, the most of it is on the other side of the end moraine. So we have this big, huge, thick sheet of ice that melts. All that sediment's going to then essentially come running downstream, downslope, especially with those rivers. So those rivers then take that sediment, and when we look at till plain versus outwash plain, which might be an example of a visual, I'll show a picture of till plain soil and a visual of outwash soil, and I'll ask you which one's outwash or whatever. And you know that till plain, essentially everything that the glacier carried, it just drops in. It's kind of like dropping the mic after a good concert. So it's drop it. Everything is just dropped in place. And so when we look at the sediment, it's unsorted. So it just kind of just dropped. Whereas the outwash plain, because rivers move that sediment, and as we've learned about rivers, I guess I already erased it. As we've learned about rivers, they like to layer stuff. The bed load, the suspended load, the dissolved load. And so when we look at outwash plain, the sediment will be layered, in which you'll have typically the heavier stuff on the bottom and the light stuff on the top. And so for those who know drugs, there's always the big nubs, the big stuff, that's always at the bottom, at the top's the shake. Same idea. Those of you partaking drugs. So I try to reach everybody. So essentially what happens is you get this layering, the heavy stuff at the bottom, the lighter stuff at the top. So we look at certain areas, outwash plain versus till plain. We can also look at the soil as far as different. Finally, the last thing is kettle lakes. So we have our big glacier. So our big glacier moved, it created an end moraine. So it created this rugged feature, but then it started to retreat. So this glacier starts to retreat. It doesn't really just head back the other direction. It just kind of melts. And so what happens is you have huge chunks that'll break off. If these huge chunks were in the water, these would be called icebergs. But because they happen on land, essentially what happens is over time, they create kettle lakes. So we look at kettle lakes. They're also going to be, on average, more often than not, found behind the end moraine. So if we think about this glacier advanced, it stopped right there, it didn't go any further. Rarely do you see kettle lakes in front of the end moraine. They're always behind it. So this is going to be something you're going to find, on average, more in the northern part of Indiana than the southern part. In fact, there are no natural lakes in the southern Indiana. The only natural lakes you find that aren't dammed up rivers are the extreme northern part, like Lake Wawasee. So we have this big, huge chunk of ice that over time, it's so big, keep in mind these are at times a mile thick where they are, is going to create a depression. And so over time, if it doesn't take enough Prozac, it's going to then fill that depression. And so what does it fill its depression with? Its own meltwaters. So essentially, it creates its own depression, its own bowl, that it then feeds the bowl, as far as being able to then do that in fresh water, then melt and fill the bowl. And so you look at the aerial view of kettle lakes, they're almost like circular, round figures. So that's what we see as far as in northern Indiana, a lot of these kettle lakes. So I had a lot of images in the previous lecture that showed, agricultural field littered with these things. And so a lot of people often confuse these with sinkholes that fill up with water from karst, but you have to know where you are. So karst isn't something found in northern Indiana. It's something you're going to find in southern Indiana. So an example of a kettle lake on steroids, Lake Michigan. So Lake Michigan, its shape is like this because the glacier moved, it carved out a big, huge depression, this cut in the surface, and then it melted and then filled that bowl. And then there's Lake Michigan, Chicago, Gary Portage. Yeah?
How would you draw all that, though? If it says describe or illustrate, like how would you?
Yeah, so that's, you could, Indiana. So at the end of that discussion, I also kind of talked about Indiana. So there's that image I included. So the end moraine, you can kind of find it like that. So you can point to that and illustrate the end moraine. And this is the Continental Glacier boundary where it stopped, creating this rugged feature that I described here in my excerpt. Then you can talk about outwash. Outwash is something that's only going to be found on this side, on average, on this side of the end moraines. All that meltwater is all melting and then heading via rivers downstream to its lowest point. Kettle lakes, like I just mentioned, kettle lakes are going to be also something that's going to be found in the northern part of the state, but once again behind the end moraine. And so the end moraine, if you illustrate, that's really, really important because that then everything is related to the end moraine. The recessional moraines, you'll see these recessional moraines kind of up here in Fort Wayne, that area, and that's essentially this glacier just heading back, and it created Lake Erie, created that big kettle lake over there. And then till plain. Till plain, much of northern Indiana is till plain, and that makes sense. The glacier came through, did all its damage, and then stopped. And so the till plain is going to be thus on that side of the end moraine. What else we got? And that's from the last Wednesday discussion. So take a look at that. That's on the Wednesday discussions. If you go to that on the bottom, I recorded that. So it's a little better than it's a little higher than this recording, but that's because the entire audience was pretty high. Yeah.
What would be the four specific stream-related landforms then?
What's that?
Just the specific stream-related landforms.
Stream-related landforms. All right. So that's another one. In the previous Wednesday discussion, what I did was I showed a particular area of Indiana, and we all kind of identify. We try to look at the image and identify where the certain features are. But here are the features. Floodplain is the first one. Then we've got point bar deposit. Not to be confused with point bar tab. Then we've got the undercut bank. We've got the Oxbow Lake. And then finally the meander scar. Is this a video lecture topic? Oh, so it's a video lecture I talk about?
Yeah.
I do? Okay, just making sure. I have no idea what I taught. So here are the features. So floodplain, point bar deposit, undercut bank, Oxbow Lake, and meander scar. So kind of we'll try to move those features there. All right. So when we look at rivers, when we think about a floodplain, where are we going to see a floodplain? We ain't going to see it up here because the water is straight downhill. Where are we likely to see a floodplain? Where the slope really starts to level out. So when it starts to level out, that increases the likelihood that a river is going to be meander, like I've already illustrated beforehand. So when we think about the general, this is the aerial view, a stream that meanders, over time, it changes its course. And so over time, it changes its course. And so throughout its different iterations or different forms, these are different locations of this river, what it's doing is it's just essentially scouring this area and flattening it out. So we look at the floodplain. The floodplain is this area here. So once again, I'm looking at the aerial view. So this is looking at the above view. And so looking at that meander over time, look at the Amazon. It always changes its course. And so what it does is it essentially carves out and flattens this area as it meanders over time. So that's what a floodplain is. The area that immediately surrounds a stream or a river, especially one that meanders considerably. Next up, let's talk about point bar deposit undercut bank, which I actually already introduced here in a previous question. So we think about a meander. So here is our meandering river. So our meandering river, so this is the inside of this meander, this is the outside of the meander. As I've already mentioned, the outside is where the water is moving the fastest. Once again, faster moving water has a higher chance of doing erosion, higher chance of removing stuff and moving it somewhere else. And so on the outside of the meander, we would expect to see a very steep slope. We call that the cut bank, or the undercut bank, whatever. It's called 10 different things, but that's the undercut bank. And it's once again on the outside of the meander. It's a very, very steep area in which erosion is occurring. Deposition, not hardly. Where is the deposition occurring? The inside of the meander. So the inside of the meander, you often see sediment building up, vegetation, all that over time, because what happens is sediment that's being eroded away is essentially deposited here on the inside of the meander where the water is moving slower. So essentially what we have is this pattern. If you look at aerials of meandering streams, it is very noticeable. The inside of the meander, you'll see almost like a sandbar, sandy material, deposit being left behind, and then on the outside you won't see that at all. That's because of, once again, the cut bank. So what we see is we can then over here, we can go ahead and predict on the inside of this meander will be a point bar deposit. Where on the outside here is that undercut bank. So as the river meanders, it's also going to leave behind these particular landforms. Now another situation that happens a lot is that rivers over time when they meander, and I've already mentioned, they sometimes change their course. And so what happens is, say this river originally was going this way, but then they had a major flooding event. The water is moving quite fast. And so essentially what happened is the river is essentially cut off from that previous meander. And so when it gets cut off, what ends up forming is this little water body that's been cut off from this meander, and that's what they call an oxbow lake. So oxbow lakes are essentially cut off from this meander. It's been cut off as the river continues on, creating a very predictable shape. And I don't know what an oxbow is, but my guess is this is its shape. So that's oxbow lake. Eventually, every oxbow lake, just like every human, we die. Every oxbow lake eventually turns into a meander scar. So a meander scar is essentially an oxbow lake that dries up. And why does it dry up?
It's not being fed by anything.
Did I lose her? I guess I lost her. Okay.
No. I'm still lost. Okay, I don't know what I mean, like, okay, I got the floodplains, like all that, but like when you start to talk about like the, whatever that river is called, I just got lost. Like, I don't understand, I guess, this question at all.
Okay. I probably go to the video lecture. Is there a certain video lecture that's from?
7.8.
7.8. Best I can do. All right, other questions? Yeah.
When you talked about the floodplains in that question, in the question it says list specific stream-related landforms found in floodplains. Does that include describing what a floodplain is within that question?
Yeah.
Okay.
Yeah. So same deal, as much as possible, for sure.
And then I have one more.
Go for it.
In the notes, when you talk about stream transportation, I think the title is fluvial processes, transportation. You talk about the sheet flow, and it talks about, and then you talk about rills and gullies. What exactly are those? Those are something that's you'll see on a future exam. But just think of it like this: when rain falls and it moves, before it gets to a little stream, before it gets to a river, it has to start somewhere. So essentially, right now, I'm creating sheet flow, as it's essentially just all flowing in one big sheet across the surface. Eventually, though, what happens is, this is going to then, as you can see, wow, this is great. Eventually, what happens is sheet flow turns into smaller little valleys, little rills and gullies, which eventually lead into bigger streams. And so that's all I was saying there is you have sheet flow, which is when it rains, it just doesn't all of a sudden flow into a river.
It starts off as one big flow, and you can see that if you look at a slope, a pavement, you can see on a real rainy day, you can see it all coming down as one sheet flow. That's its name, one sheet of flowing water that comes down a slope. But then eventually it fills into little smaller rills and gullies which flow into streams. All that was saying as far as looking at drainage basins, where do they start from? Just like we start from our mother's womb, where do rivers start? Where do they begin? So I guess that's kind of a deep question anyway. Yeah. Yeah.
Can we talk about the islands along the Atlantic coast?
Yeah, barrier islands. So barrier islands. So this we can also come back to fluvial processes, because whenever you talk about all these processes, we talk about the fluvial processes. We have to talk about this chain reaction, this chain of events. We've got erosion, which starts, and then transportation, which moves that eroded away material, moves that erosion, and eventually transports it and lays it down. So we have erosion, then transportation, then deposition. So all the various processes, whether it be aeolian processes or wind processes, whether it be glacial processes or fluvial processes, they all have those same three characteristics. They have their initial erosion or weathering that breaks the material down, and then the various other processes that move that transportation somewhere else and eventually lays it down. So that's then deposition. So we can apply that to the barrier islands off the Atlantic coast. The first thing about barrier islands, they're always on the trailing edge of a moving plate. So we're never going to find them along the west coast. Why? Why would we never find them along the western coast of the United States, barrier islands? What's up?
It's the leading edge of the plate.
Because it's the leading edge of the plate. So essentially convergence is obliterating. It's, those barrier islands don't have time to even form because you get convergence. You got plates that are colliding into each other, and essentially those barrier islands can't ever form. So it's always on a trailing edge of the plate. And so once again, right through the middle of the Atlantic, we've got that separation that's occurring. And so what's happening is the Atlantic coast of the United States is moving that way, as we had that separation, that seafloor spreading occurring in the Atlantic Ocean. And so we're always going to find this along the trailing edge of a moving plate. In particular, we find them along the coast of the Atlantic, but also to a certain extent over here as well, off the coast of Texas. So how do these suckers form? So this is very interesting. So if you've been to Atlantic Beach, Outer Banks, Virginia Beach, Outer Banks, Myrtle Beach, what a dump, Hilton Head, Daytona Beach, another dump, all those various beaches. What happens is if you go there, you note that when you go on the mainland, you go over a little bridge and you go onto the narrow strip, the narrow island, and those are barrier islands. So once again, barrier islands, trailing edge of a plate. But if we look at their shape, so if this is a coastline, their shape is typically very much parallel to the coastline. Very thin, narrow shapes. So how do these suckers form? So first off, we have to think about, well, what's going on further upstream? Because these are fluvial processes, it's created them. And so further upstream, we've got the Appalachian Mountains. Which, do the Appalachian Mountains look like that today? No. The Appalachian Mountains were the oldest mountain chains in the world. They used to look just like the Rocky Mountains. But over time, they've been worn down, they've been beaten down, they've been eroded and weathered away. And so a lot of that sediment is no longer there. And so all that sediment has to go somewhere. It just doesn't go into outer space, just doesn't disappear, doesn't go into the sky. What moves it is rivers. So then we have rivers that then move that sediment. So we have erosion happening over here, up here in the mountains, erosion, and then over time transportation because of rivers that then transport that sediment to the coastline. So if we zoom in, we look at this view now, rivers take it to the coastline. So that sediment's eventually dumped out into a sea. And just kind of dumped out into an ocean, big ocean. But if you notice, these shapes here aren't the narrow shapes that actually are barrier islands. When you go to an ocean, when you go to the beach, you always notice the waves come crashing in. And so if you can think about the counteracting influences, so we have fluvial processes bringing that sediment to a coastline, the counteracting influences of a crashing ocean and all of those waves help to create these very thin, narrow shapes. of these barrier islands. And so essentially, the barrier islands, all those beaches I just rattled off, are built on sediment that was carried all the way from the Appalachian Mountains. And so that same sediment, that is the underlying, what those condominiums and hotels are built on, is essentially sediment from the Appalachian Mountains, in which we have erosion up here, transportation, and eventually deposition, in which that sediment is laid down, creating this chain of islands. That help?
Yeah.
Could you also talk about like immersion? Because that's another theory that was in the book about like a plate emerging from under sea level. Is that something that was introduced to that?
Yes. The barrier islands here, I don't know how much was that mentioned in the barrier islands? I don't know that term that well. IMMERSION?
EM.
Oh, yeah.
Yes.
Don't know that term.
Just out of curiosity, you mentioned that Long Island is an end moraine. Is it getting bigger due to barrier island effects at all?
No, essentially Long Island is the transition. All islands south of Long Island are all barrier islands, whereas all islands are all, like we mentioned last time, I mean, it's an island, but it was actually an end moraine that's been filled up around it. So Cape Cod is like that. You also have a lot up in that area in which you just have parts that are kind of broken off, and historically it's been broken off, rugged coastlines and all of that, in which erosion helps to break it open and separate what was once a peninsula might be separated into an island that's kind of left because of that cutoff. But the Long Island's pretty much the cutoff.
Curious.
And I'm wondering now I think about that if the end moraine kind of removed a lot of the barrier islands. I bet that's the case. Those barrier islands probably always have been along that coast because the Appalachians go all the way up into Canada.
Yeah, that's
so the same kind of things going to occur. It's just the end moraine, like all glaciers, just essentially removes the previous layer. That's where geologists go back in time and try to figure out, well, what was something like before a glacier flattened and removed a lot of stuff from there. Like, for example, the woolly mammoth. A lot of them we don't know because its bones were just essentially flattened and obliterated by the glaciers. So we kind of think we know based on some cave paintings or something, and some peyote too, kind of figure out something out of the two of those. Next. That answer? Yeah. You can find me for not knowing that if you want. Next. Any other questions? Is that all of them? All right, so I'll be around 1 to 3 and 3:30 to 4:15-ish on Wednesday. Go ahead and write that down. 1 to 3 and 3:30 to 4:15. CA 213B. Now I'll make an announcement, but Wednesday will also be the last day I'll sign for withdrawal. So I don't know who that would affect, but it's the last day I'm willing to sign for withdrawal. After that, whatever grade you get is the grade you get. I'll explain that later in an email as well.